Hello, everybody, and welcome back to Coffee Break, the show where we break down interesting topics all within the time it takes you to enjoy a few cups of coffee. As always, my name is Clifford Swartz, and today I'm joined by a very special guest, Dr. Smith. How are you doing?
I'm doing good, Clifford. Thank you.
Of course.
Thank you for having me on this morning.
Absolutely, it's a pleasure to have you. So, Dr. Smith will be talking to us about how to replace all of our Hall effect sensors, positioning sensors with inductive position sensors. But before we dive into that topic, I'm going to throw it over back to the booth to Michael Pierce, and he's going to tell all you people how to participate. How you doing, Michael?
Great, thanks, Clifford. So, welcome to this discussion. It's going to be another great one. We're broadcasting live on LinkedIn, Facebook, and YouTube. So please submit your questions in the chat, and we'll try and answer them after the discussion. Also, if we can't get to you, please email us at livestream@microchip.com, and we will get back to you afterwards. Always, please just share this presentation with your colleagues and friends because we'd love getting additional people on these chats. And back to you, Clifford.
Absolutely. Thank you very much, Mr. Pierce. Can you talk to us a little bit about what an inductive position sensor is? For the folks at home that may not be familiar, or those that are only familiar with Hall effect sensors, what's it all about?
Yeah, sounds good. Thank you, Clifford. An inductive position sensor is really a magnetic sensor that does not require a magnet. So we've replaced that magnet. Instead of using the magnet as the target, our inductive position sensors use a piece of metal. You can actually see it on the slide up here. There's the microchip IC, and the sensor itself is the PCB board. So we have traces on the printed circuit board that are positioned so that that metal target, that whether it's a rotary angle that you're trying to do or a linear movement that you're trying to measure, we can precisely determine the location of that piece of metal. So it's a magnetic sensor, but it doesn't require a magnet. And one
Interesting.
and here I'll show you a demo. I got one in my hand up here, and I'll show this to you, and we'll show it on the screen. You can see right here, this is a linear sensor. This is a 100 millimeter linear sensor. There's our IC, right? It's tough to see. Not looking at the camera. There we go. It's
But
tough
I
to
can
see
see you.
real easily there. And then you can see that piece of metal is moving back and forth, and then we got our GUI, our integrated IPCE software that's picking that up and showing you the position. So we're generating a magnetic field. We have two receive coils that are there that are receiving that magnetic field, and this piece of metal is disturbing it. And this IC, the microchip IC, is calculating, identifying, and triangulating the precise location of that sensor.
Cool. So what do we see in the marketplace currently? I know on screen we have Hall effect sensor, but what is going on in the actual marketplace?
Right. So there are a lot of different position sensors, a lot of different technologies, and clearly, Hall effect sensors has been there today. And what we're seeing is that this is an alternative to those magnetic-based sensors. And one of them is a Hall effect sensor. Another one might be a TMR sensor or an AMR sensor. We're removing that magnet and replacing it with a piece of metal. And this technology has some really neat advantages over that.
Do you mind diving a little bit deeper into what those advantages are?
Sure,
Thanks.
sure. And the big three are that with inductive position sensors, we can be more accurate. We can be immune to stray magnetic fields, and then we don't need a magnet in the system. So why are we more accurate? And really the simple way, the answer I like to give and show is that we aren't using magnetic material. We use a piece of metal. And Hall effect sensors require that they precisely know that magnet's property, and then that magnet's property changes a lot with temperature. So it's difficult to get accurate results over temperature. Inductive position sensors remove that completely. Our algorithm is independent, at least at a first order, temperature. And as a result, we can be very good accuracy over all temperature ranges. The other one is noise immunity. You know, in today's environments, there's lots of stray magnetic fields that are around, if it's a motor or a solenoid, and our technology can be immune to those types of stray magnetic fields. And the way we do it simply is we filter out all those magnetic fields that are outside of the magnetic field that we generate. And the way we do this, it's like AM radio. We have a fixed, we excite the primary of our winding, with a fixed frequency, and then we do synchronous AM demodulation to filter out the other frequencies. Much like your AM radio. Your AM radio, that antenna is picking up, the whole AM spectrum. But when you on your tuner,
Dial, yeah.
you're dialing in right to the channel that you're interested in. We do the same thing. And the other one, of course, is no magnetics. So you don't have to worry about sourcing it, the cost associated with the magnet, and now you could just use a piece of metal in that case, which is a fraction of the cost.
Nice. And so the final part of that equation is all of our reference solutions and all the different tools and guidance that we offer, right?
That's right. Yes, we have some reference designs, and we'll talk about that a little bit about on our website. We're going to help you design that PCB layout because we sell that IC. We help you design that PCB, how those traces go to fix that sensor design.
Cool. So we've talked about how it's really, really good in high temperature situations. It can be placed in environments where there are other magnetic fields. And a lot of the graphics that we're already showing have car-related things. So from my perspective, this reads as a perfect match for automotive. Is that right?
That's exactly right. In fact, in a car, there are many, many types of position sensors. And this graphic shows all the different types. And
that's a lot.
These are great places for inductive position sensors. Your accelerator pedal, there's 2 position sensors in there that are sensing the angle that you're putting down, whether you're lead foot or not, it's sensing that angle down for you, giving you 2 sensors in there. And that could be an inductive position sensor, and probably it's a good chance it already is. There's a transmission gear as another possible example. Gear shifters, steering angle, your chassis height sensor. These are all examples where inductive sensors, position sensors work very nicely. You can notice throttle body, stuff that's where it's high temperature, what we call under the hood, where the temperatures go really high, but you're still needing to handle and measure position. That's a good place for inductive position sensors.
So automotive, from my perspective, seems like an absolute slam dunk with this technology. But what other sort of industries do we see inductive position sensors really shining?
Yeah, the industrial market is another area where we see this working really well. Robot control, your robot control, there's many axis of rotations. Each one of those axis of rotations is an opportunity to put an inductive sensor to measure that angle precisely. A joystick, there's industrial joysticks, or an industrial rotary encoder where you need to be immune to harsh environments, temperature, dirt, even a potentiometer replacement solution on mixer boards where you're worried about dust or sand or liquids that could be spilled inside the mixer. This is all can be immune to that.
Nice. And so this seems incredibly far-reaching, very broad. Any place where there's a Hall effect sensor, this technology kind of fits. Where can people actually go to get started if they wanted to design with this technology?
Great. Yeah, thanks, Clifford. So on our website today, we have a place where we've really made it simple to dive into the technology. You can simply download. We have 4 sensors today, and we're building those. We'll have more in the future, but you can download an Altium layout of the PCB traces that go for 2 rotary sensors and 2 linear sensors. You can download it. You order a particular IC. In this case, it's the LX3302 AQPW-EZ. And then you put it on your board, and it's a plug-and-play solution for you. You just attach to the right signal at the output of that IC. You put the target at the right position, or you position that target, and then you're going to get position coming out of it. So we've really made it so that at least at this first step, you can be plug-and-play type solutions.
Right.
Now, as you're saying, as you dive deeper in the technology, that first step was, hey, you don't even need to read a data sheet. That's our goal on that one. But here, on this next step is now you want to dig deeper into the technology. You want to find get the best performance out of it. That's where we have evaluation boards, we have programmers, and we call our IPCE 2.1 software that's available. It's called an Integrated Programming and Calibration Environment. This is where you can actually measure the sensor. We've made it simple so you can measure that sensor, you can calibrate and customize the sensor and the IC to fit your particular requirements. We also have an advanced debug mode where you can go in and look at the inside nodes inside the IC to really fine tune your sensor and get the best performance out of it. So these are available for us to make it easy for you to really get started in the technology.
Cool. So like people can see at the very bottom of the slides, we have a link, and we're going to have links in the bio and in the comments and everything that you guys need. But if people want to know more, I believe they can go to microchip.com/inductive position sensors, no hyphens, and that'll be a vanity URL that'll take you right where you need to go. Beyond that, is there anything else you want to plug, Mr. Smith, Dr. Smith, before we go into viewer questions?
Yeah. Yeah, I think you appreciate it. What we're doing here at Microchip, we're really excited about this technology. We love sharing it. We love teaching it to our customers. We hope that you get excited as much as I am at this technology, where you can get rid of your magnets and instead just use pieces of metal for the advantages we talked about. Thank you.
Absolutely. Cool. Well, Mr. Pierce, it's your show now. What sort of questions do we have from the viewers?
Oh, yeah, tough question.
Hopefully.
Well, actually, one from me first. Many, many years ago, I actually used to work in automotive instrumentation, and we had a lot of sensors that were basically in like fluids. So like we had transmission picks up that were Hall effect based in the transmission itself. How does this technology work with surrounded by fluid with big gaps?
Exactly. It actually, as long as it's not conductive, the magnetic field is going to run through that very well. Liquids, oil, these are things that are not conductive in nature. They're not going to be affected by the magnetic field, and so you can be placing these solutions inside of those types of liquids and you get accurate measurements out. Whether it's a linear sensor that you need for a brake fluid level, or you want to do it for a particular liquid level, you can do that. Those are definitely anything that's not conductive can be used with this technology.
Okay, and we have one in from Alec. Are the demo boards available, and where do I get them from?
Sure. And so two places. The link that we're going to provide at the end will have our getting started page, and there's a whole list of demo boards we have that are available today. So we call them evaluation boards that you can buy individual sensors. We have a kit you can buy. There's also coming in the future, there'll be a nano kit and click boards. These will be available in the future too. So that's available on our web, and those have the links. The other place is Microchip Direct. You can just type in the LX3302A QPW-EZ part number, and you should get a list of tools that can work with, that you can purchase right from Microchip Direct on these devices.
Cool.
Yep. And we have one from Claudia. So what design resources are there to help me design a PCB layout using your sensor chips?
Right, and so the best design is the one I showed you, and that is you could just download those designs right from our web. So we have 4 designs today, and those should fit a lot of applications today. As you get more into the technology, you want to customize it for your solutions. There are instructions that'll be available on the web, and also you can talk to your Microchip sales representative, and we can get you and target a particular application sensor just for your particular needs. So those are available too.
Yep. And another one from Ashish. How small can the sensor be?
That's a good question. I showed you it's really flexible. So I showed you this sensor. This is a 100mm linear sensor. And you remember what we're doing is we aren't using a magnet, but we are using a piece of metal. But the trade-off is that we put traces on that PCB board, just like I showed right here. And so we could be really small. Like for a rotary sensor, on our website, you'll see an example of a 15mm diameter rotary sensor. We've even gone smaller than that. Or on the other hand, if you want to measure a linear sensor that's maybe 3mm, those can be made. Or you could build a sensor that's maybe 600 millimeters long. These are examples where we can be very flexible on the size. It does take PCB space, but what we've seen and what we've been able to do is show really small designs, so they can be really small, 15 millimeters. Hopefully that answers your question there.
Cool.
And we have one from, I hope I pronounce this right,
You got it.
Ramandeep. Is there a way to filter vibrations that might be picked up by the metal piece?
Hmm.
Okay. Well, the IC is one is of course you can, but I'll tell you that that metal piece, we have an AGC on our front end of our IC. It's an automatic gain control circuit, and it's really designed to be able to adjust, and if there is an air gap change, to automatically correct for that up front. So that is built into the IC. Now, our chip is very flexible. You can actually turn that off, and we can actually transmit that information, that gain control, back to a host microcontroller, and then you can do any sort of processing you need at that level. What we found is that small vibrations really aren't being picked up, or are pretty much insensitive for this technology. But we can explore that further if if you want, and get me your contact information, and we can talk about it later too.
And here's one from Paul Tan, and I'm going to rephrase it a little bit. Can you talk about the differences and advantages of your products versus competitive inductive position sensors?
Right. And so, I would say that we are very good for accuracy. We have some neat features, very flexible for your particular application. So our accuracy is quite good. And the way we do the accuracy, why it's important is, hey, one, I've showed you that the sensor design, and we have some big sensor designs that can do it. That traces on the PCB board. But inside the IC, we have automatic gain control on the front end. We have static compensation, calibration that's done, but we also have dynamic compensation. And this is unique, that no other supplier has, where we can then understand and identify variations in the air gap and use that to change our calibration points. That's all when you're trying to get to the ultimate types of accuracies over large temperature devices. And these are things that are unique to Microchip's solution.
And we have another one from Jared. Can you use an alternative to FR4 PCB, perhaps a flex PCB or regular wire that's formed into the required shape?
Oh, for sure. That's no problem at all. FR4 is not a requirement. It's a simple device, but you can do other types of things. Flex circuit is very possible, and those are just as fine. Maybe it's over an arc where you're trying to do, put the sensor over an arc and have the target be, you're measuring a metal target in an arc shape. That's possible too. So, we've just started we've kind of given some examples out, but really, you guys, you guys probably are the creative ones. The audience is the creative ones, coming up with even new places where you can put that. But to answer your question, yeah, FR4 is not a requirement. Flex PCB is a good one too.
And we have the last question from Enrique. What type of metals can be used?
Yeah, it's a good question. So really anything that's disturbing the magnetic field is a material that can be used as a target. And I assume it's for the target, what metal can be used for the target. But the ones we like, and the ones that get the best, what we call air gap, the distance between the metal and the sensor, is aluminum, copper, and stainless steel. But really anything can be used other than outside of that that's conductive. And those three metals are the ones that get the best performance. And the other thing that I want to point out is that the thickness of this piece of metal can be very, very small. We're talking like the thicknesses of 1 ounce copper is enough to make this a viable high performance target. So there's really no thickness required on that piece of metal.
Cool. No more questions?
And yeah, that's it.
Well, if there's no more questions,
Okay.
Mr. Pierce, I have a joke for you before we close things out. How does an engineer drink coffee?
Oh, that's a tough one. I got to say they download Java.
They install Java. Good job. So that brings us towards the end of the show. They asked me to do a joke, and I'm delivering. Dr. Smith, thank you very much for coming on. You've been a
Thank you.
blast. You've been phenomenal with all the questions. We'll let you get back to surfing whenever you want.
Yes.
For the viewers at home,
Surf's
make sure
up.
to go to microchip.com/inductive position sensors. And in 2 weeks, we'll be doing another show where I'll be talking to you guys about how not all compilers are created equally. So be sure to tune in for that. And finally, stay happy, stay healthy. Thank you to everybody in front and behind the camera. And we'll talk to you in 2 weeks. See you.
Bye.